Okay, this video is going to focus on hyperbolas. This is our fourth conic section. We've talked a little bit about circles, talked about that a bunch in the past, talked about parabolas, talked about ellipses, and hyperbolas are the last of the conic sections. Okay, circles is a single set of points equal distance from a single point, radius. Parabolas are a set of points equal distance from a point and a line, focus and directrix. Ellipses are a set of points equal distance from 2 points. The hyperbola, the final one, is going to look like this. It's a set of points where the difference of the distance between the points is equal. So we'll call this A and B. B minus A, not B equals A. B minus A has to be equal to CD, C minus D. For any sets of lines connecting the foci, again, these are foci, to, or connected to the, from any point on the ellipse to the two foci. That does apply to, let's say I cross over here. E minus F as well. Okay. These ones here are called the vertices. This right here is called the conjugate axis. And then right down the middle, perpendicular to the conjugate axis, is an axis of symmetry. And the hyperbola is going to look a lot like the ellipse. So standard form here is going to be x squared over a squared minus y squared over k squared, or no, over b squared, equals 1. And this is horizontal. Putting on a graph, looks like this. H and k could be in there. For today, we're not going to use an H and K. Those dashed lines are asymptotes. We'll talk about how to get them. That's your horizontal one. Okay. Okay, so that is your horizontal ellipse. Your vertical, because I'm doing a minus, I don't just stay with x squared first, like I always have been. So this is a vertical ellipse. This is going to open. We'll talk about how to get these asymptotes in a second. This one's going to open this way. Notice that the a squared stays under the first one. That's going to matter. Okay. So for this, your asymptotes, if they're centered at 0, 0, plus or minus, they're equations for lines. Slope is positive b over a and negative b over a. There's 2 of them. These ones, because y is on top here, or a is under y, it's plus or minus a over b. So because we switched that. A, this distance here is a, this distance here is a. Okay. A is the distance from center to vertices. And then the foci, again, we're going to do, this time we're going to do c squared equals a squared plus b squared. Again, that's true for both of these. So let's do an example. We have a hyperbola centered at 0, 0. We know it has vertices. They kind of did it this way, plus or minus 4, 0. And foci, so they're putting the plus or minus, that's 2 points, positive 4, 0 and negative 4, 0. Has one focus at 5, 0 or foci at plus or minus 5, 0. So this is moving along the horizontal axis. And here's my foci, or vertices. And then my foci, let's make those red, are out here. Okay. First thing I'm going to do here is find b. So I know c squared equals a squared plus b squared. And c, distance from center to foci, focus or foci is 5. A squared is going to be 16. And so b squared, when I solve this, is going to be b squared is 9. That's not 16 squared. It's 4 squared. 4 squared, which is 16. That would be much more sensible. B is 3. What that means, and I'm going to make it for drawing. This is going to help me draw. I make a box here. 4 horizontally, 3 vertically. My asymptotes are going to go through the center and the corners of my box. And here is my hyperbola. This pink thing. To write the equation, this is horizontal x squared over a squared. A is 4 plus or minus 4, or a is 4, I guess. Just take the positive one. 4 squared is 16. B is 3, b squared is 9. There's my hyperbola. You can sketch the hyperbola. Checking with a graphing calculator. You can check with Desmos if you want, but you cannot check this with the graphing calculator. Desmos, however, can take that equation straight up as it is. So let's take a look at a hyperbola. Not quite in standard form yet. And we're going to graph it. We're going to talk about everything it is and graph it. So for starters, I need to get it to standard form. So I'm going to divide everything by 63. And then I'll reduce. Hey, 63 is 7 times 9. Hey, cool. These are going to reduce out nicely. Y squared over 7 minus x squared over 9 equals 1. Standard form. So I know that this is a vertical one. Okay. I'm just going to graph it right away because I think that's going to help me with my analyzing it. I'm going up and down 3. No, I'm going up and down square root of 7. Square root of 7 is more than 2, less than 3. It's more than 2.5. Somewhere in here. I'm going to go 3 left and right and make my box. And then I'm going to draw my asymptotes on here. And finally, I will plot my hyperbola. Interesting things I can talk about my hyperbola are the asymptotes. And this one is A over B. So my asymptotes are y equals plus or minus, these are two lines, square root of 7 over 3 x. For finding my foci, let's do the foci in green. I know that c squared equals a squared plus b squared for this one. C squared, I know a and b. A is 7, b squared is 9. So c squared is 16, c is 4. So there's my foci here on my graph. And that is 0, 4, 0, -4. Vertices, those are in my graphs. 0, square root of 7, 0, -square root of 7. And that's about as much information as I can give on that. Okay. Modeling with a hyperbola. And then, oh, one last thing here before I move on. Eccentricity, just like what we talked about with the eccentricity for an ellipse is always a number between 0 and 1. Eccentricity for a hyperbola, I believe, is more than 1. Yes, it's more than 1. E again is still c over a. But this time my c, a is always this distance in here. And c is the larger distance here to here. This is going to be more than 1. Okay, so communications. The graph of a two-dimensional view of a satellite dish. The focus is located at f1, but the receiving device is located at the bottom of the dish at point f2. The rays are reflected by the first reflector, blank curve, towards f1, and then reflected by the second reflector, blue curve, back to f2. Okay, what kind of curve is the second reflector? So the second reflector is a hyperbola because it reflects rays aimed at its internal focus towards an external focus. So that's an interesting property of hyperbolas. So parabolas reflect things towards their internal focus. The outside of a hyperbola reflects things back towards its external focus. So if I reflect something in here, it's reflected towards the focus over here. Okay? It's actually the focus on the other side of the ellipse. But if I take that ellipse away, if I have just this side right here, this left thing as an elliptical shape, anything off the outside will be reflected back towards the inside. Okay. So this one says the vertex of the second reflector is 3 inches from f1 and 21 inches from f2. So I've got f1 here, and they've got a reflector drawn here. This is an ellipse. They told me that's 3. They also told me that this is 21 over here to f2. What is the equation for the second reflector? Assume the conic is horizontal and centered at the origin. So I know that centered at the origin, this total distance is 21 here. Its total distance is 24. So I know that I'm going to center this at the origin. That's 10. I know this vertex. That's F1. This is F2 over here. That should also be 10. This here is my hyperbola. So A equals 9. C equals 12. And I know it's a horizontal, so it's 12 squared equals 9 squared plus B squared. 144 equals 81 plus B squared. Subtract 81 from both sides, and I get 3. 63 equals B squared. So a positive note, I don't really need B. To write this equation, I need x squared over a squared. A squared is 81. Minus y squared over b is square root of 63, but I don't care because I'm just plugging it, I'm squaring it. And this is my equation for my ellipse. Okay, that's an introduction to ellipses.